Hello everyone, welcome to another video. In this one we're going to be talking about a topic in physics known as projectile motion. And this is the analysis of motion of objects. It's pretty straightforward, so we'll just get started. As you can see here, we have a skateboarder, a skater, if you will, and he's jumping off of a cliff. So you can see with kind of like each successive image that I've drawn, this is basically the skater at different times. But the spatial coordinates that we show in the schematic are actually x and y. So the first thing we always want to do is label our coordinate system so that people know which way is up and which way is down. Okay, now with that said, we are given some tasks here. So we're going to label the schematic. This is going to involve choosing an inertial reference frame. And that's basically choosing where our data begins. What is relevant for the problem? Well, in order to determine that, we have to actually look forward to what the problem is going to ask us. And so we're asked for how much time the skateboarder is in the air. And we're given values for the gravitational acceleration. This should be negative since we determined that up is positive, and we know that gravity acts in the downward direction, so that value will be negative. We're given an initial velocity of the skater as well. So and that kind of, I guess that tells us where our inertial reference frame should be because we're analyzing the skater in flight. And so we can say that our datum can start like right here where he launches off the cliff. And then we can also just define, I could choose X to be up here. However, I'm going to choose it to be down here because I feel it is more intuitive that way. We'll still end up getting the same answer, but it just simplifies the calculations and it's easier for me to think about. So we label our spatial coordinates. What else can we know? It says that our initial velocity, so the velocity vector here is going to be tangential to the surface that he's taking off from, right? So I actually drew a close-up of this right here, and you can see that the angle theta that is formed with the horizontal axis, remember, he's not just dropping off, he's kind of ramping off, right? So we have to figure out essentially what the horizontal and vertical components are here. And since there's an angle associated with it, we know that a factor of cosine will be required for the x direction, and a factor of sine will be required to get the velocity in the y direction, since there are two components here, right? There are two velocity components. So we basically have, I'm exaggerating the angle here a little bit, and then we just use our triangle rules, and then we'll also be utilizing the kinematic equations of motion. These will be very helpful in determining the final landing location, which will be somewhere along here on the x-axis. And so to get started, let's just, we have to find the time, right? So what we're going to do is we are going to start where the skater starts. Our initial velocity, Vx naught, is going to be 25. And I'm going to type this in on the calculator. I did not work this out before, which I should have. We're given the angle of 14.1 degrees from the horizontal. Ooh, I'm in radians. I need to go back to degrees. Make sure you're in degrees for this on your calculator. We get to 24.4. So that's the velocity that we're moving. The skater is translating through our reference frame in the horizontal direction, not at quite 25 miles an hour or meters per second, but at 24.2 meters per second. And then we can perform a similar calculation with sine, and we get a much smaller number, which makes sense too. His change in vertical location isn't changing as fast, and we get a value of 6.09 meters per second. So these are the velocities with which he's going to launch off of the cliff with. Okay, and then also we need a height. We can't know anything without height. So I'm going to say delta H, that looks to be about maybe 20 feet, right? Or what is that, like 6.2 meters? We'll say 6.2 meters. We're neglecting air drag. That's typically how we approach these projectile problems. Because that force is going to be kind of negligible when you have like a massive object. He's not going to encounter a lot of resistance. His velocity in the horizontal direction is not going to change according or for the purposes of our problem statement. In other words, that's going to be the velocity the entire time he's in the air and throughout our analysis for the x direction. But the y direction has to change, right? And if we think about what's going on here, if we just draw like a little diagram, we say, okay, well, let's just draw the skater as a point particle. And then what happens is he goes up a little bit, but then he's going to go down a lot, right? Because he's got to fall off a cliff. And so basically our y is going to go up to some maximum. And then it's going to be, because we set the x-axis as the bottom, this value right here where he lands is going to be 0. And that's why it shows that. You can see why that makes it much easier. We know that the height from here to here is 6.2 meters. And then how much does it go up? Okay, so we have to find the maximum value of this parabola. And so to do that, we basically put this curve on an axis. We're going to find the landing location and also, but first we have to find the maximum location, right? Well, we know that this projectile, this skater, is in a gravitational field of negative 9.81 meters per second squared. So if you think about this, every second his velocity is changing by this amount, right? Well, it turns out that the amount of time that it'll take to get to 0 velocity from, we're basically looking where, okay, where's the y velocity equals 0? It's right here, right? And so what we're going to do is find the amount of time basically from launch to this maximum point here. We're going to find the time associated with that portion of the flight, and then we will analyze the second half, and it will be much easier. But for now, we say that this is the initial y velocity, and we are decreasing 9.81 meters per second squared. So that means that it's going to take us 6.09 meters per second divided by 9.81 meters per second squared. That's how much time it's going to take for us to get to 0 velocity. .62 seconds. 61 seconds. All right. And let's just make sure our units check out. It looks like one of the seconds cancels with this one, and then the meters cancel. And then because this is in the denominator, it goes up and we get seconds. So, all right. For the first portion of the flight, we have 0.621 seconds. Now, we're going to add that to whatever we get just falling from... Oh, and we also have to figure out the height that we reached now. So, we can use our equation of motion here, and we can say Vy equals Vy naught plus, and then since A is our acceleration, or G is our acceleration, we can replace A in our equation with G. And we wrote that it was negative, so it'll be positive in this general equation, and then I'll sub in the negative. Okay, and so this is our equation that will give us the time. We have the time. We need it when Vy is 0. Solving for time, we get negative V YO over G, which is actually what we just did. So that is why that equals that, but the position now, we'll call it Y, equals Y naught plus V Y naught T plus 1/2 G T squared. And we have all of these values now. We just need the maximum height. So we know Y naught, that's 6.2 meters. We know Vy naught, which we calculated right here at 6.09 meters per second. Let's write our units. Our time, 0.621 seconds plus 1/2 negative 9.81 times 0.621 seconds squared. This is meters per second squared. So those units cancel. We end up getting meters for that term here. And then also the seconds cancel here, and we get meters for this term as well. Punching this into the calculator is going to give us our maximum location here. Sorry I didn't work this out ahead of time. I just kind of thought it would be a cool concept to explore, but then I picked a bunch of weird numbers. Negative 9.81 meters per second squared times 0.621 squared. Okay, I get 8.09. Okay, so we go like up an additional 2 meters. So on our little schematic here, we have got the y location. Remember, I got that from setting v of y equal to 0, knowing that at the maximum height, the object has to reach a 0 velocity before it transitions from a positive velocity to a negative one, just because of the continuous nature of projectile motion and really our classical understanding of physics. Great, so we've got that down. Now we just need to figure out the time it takes to fall from 8.09 meters in a gravitational field that is given this value. Okay, and I think we can do that just by, let's see, which one of our equations gives us what we need. So we need to find the time that the object falls 8.09 meters. Looks like we have a position and time relationship, which is this top equation here. But we're using y's, right? So instead of x's, it's y. So really, we're just using the same equation that we just used, but now we have an initial height. Let's see, y max. Put that, and then the velocity in the y direction for this part starts at 0, right? Because we've already taken care of this region here. So our initial location is at the maximum location, where the velocity is 0, and then so all we have left is 1/2 gt squared, and then we can solve for the amount of time that it takes to get to the bottom. Oh, and also, this is where I was getting confused just now. The bottom is at y equals 0. And so our final velocity in this case is 0. This is 8.09, which means that our t just equals, I can solve for t. I was just kind of nervous, but we have the square root of 2y max over g, I think. And then if we plug that in, we just get 2 times 8.09 divided by 9.81. And I got 1.284 seconds. And that's just for the second interval. So the total time he's in the air, you have to add this to that. So 0.621. And that's going to give me time total. 5, 10, 9, 1. So our total time in the air is 1.905 seconds. And that concludes part B. What's the impact speed? Well, I gave you a hint here. What's the impact speed that he hits the ground with? So when he hits the ground, looks like he's coming down on it with some angle, theta, right? And that must mean there's like a velocity vector associated with this. It's got both Vy and Vx components, but we already said that Vx here, Vx final equals Vx initial because we're neglecting air drag. But Vy is going to be different than it was at the start. And so let's figure that out. Vy is 0 right here, so we can just analyze the second half and use our equation of kinematics to figure this out. So we want to find Vy final. It just equals the initial velocity in the y direction. We're starting at the maximum height, so that's 0. And then plus gt, which we already know the values of. That's negative 9.81, and this is the time that we just got, which was 1.905 seconds, right? 1.905 seconds. And this is cool. This is good because we're going to get a negative value. In fact, the skater has a negative velocity because we defined our coordinate system to be positive in the upward direction. So our sign convention is checking out, which is pretty cool. And we get final velocity in the y direction of negative 18.68 right, meters per second. All right, well, I gave you this relationship here. We know that Vx is equal to the initial Vx, which was just the 25 cosine of 14.1, 24.2 meters per second. Remember, we're not losing any energy to air drag because we decided to dismiss it, which you will find is the case in a lot of these problems. So the impact speed is given by 24.2 squared plus, and then whatever that velocity was, 18. And even though it's negative, because this is a magnitude, this square root of the sum of the squares operation that you'll do in magnitude calculations, it basically just disregards all negative signs. How do you get the magnitude of V? In other words, you can call this magnitude of V. And if I type that into the calculator, I will get my final answer, which is 30.58 meters per second. So the skater hits the ground with this velocity, the x and y components of the velocity combined that we figured out in all of the previous steps by kind of just following the path of the skater. And so I hope this video was helpful to any of you physics students or anybody who is thinking about going into this. It really is a fascinating subject, and it gives us the power to predict the future, quite literally. So very interesting topic to get into. Make sure to like and subscribe to my channel if you enjoyed the video, and leave a comment on anything that you want me to discuss, or if you have any questions about this video, I would be happy to oblige. Thank you for viewing, and I'll see you in the next video.